Hello and welcome back. So, we talked about the center. Now let's talk about the spread, okay? This lesson is on measures of variability. So, we're going to talk about the general problem. Then we're going to talk about three measures of variability: range, deviation, and variance. I wonder if we're going to talk about standard deviation. And then we'll talk about how we can visualize dispersion or visualize variability. So, the general problem is that central tendency only deals with the center of the distribution. We know what the mean is, but we don't know how far away um, the data tends to stray from the mean. And so data can be very close to the mean and have a small standard deviation. We're going to specifically talk about what standard deviation is. Or there can be a large standard deviation where, yeah, there's a mean, there's a center, but maybe there aren't a whole lot of data points at the center. Some definitions: dispersion or variability, how much the data points vary around some center point, usually the or midpoint, usually the mean, and it's the spread. Okay, like you think of things getting dispersed. They're spreading out, right? And this helps us convey more information about the data than just the central tendency. First of all, the range, the most common thing that we think of when we think about how data is spread out is the range. This is the distance or difference between the largest and smallest score. So when we're using the term range in everyday language, usually we say, oh, the temperature today is going to range from, and we give the minimum score and the maximum. The minimum temperature and the maximum temperature. So I might say, oh, the temperature today is going to range from 30 degrees to 60 degrees. So yes, we'll need our coats in the morning, and then in the afternoon we can take them off. But when we're talking about the range in statistics world, it's the maximum minus the minimum. It's how many degrees separate the maximum and the minimum are. So, for example, we would say that the range is 60 minus 30, which is 30 degrees. The range is 30 degrees, okay? This can be influenced by extreme scores, right? So if in the middle of the night it's going to drop way down, okay, but it's not going to stay there very long, let's say, that can influence what we would say the range of temperature is going to be today. Different samples of the population can have very different ranges. Range tends to be a bit unstable, and so it might not be the best estimate of a population overall. All right, because we can only grab a sample usually. It might not be the best estimate of the population overall because it can be a little bit unstable. Now, the interquartile range, here we're going to deal with those extreme scores by getting rid of them. We're going to delete the lowest and highest 25% of the scores. And the interquartile range is what remains. So it's the middle 50% of the sample. Okay, the 25th to the 75th percentile is the interquartile range. And so let's say I was giving a test and about a quarter of the kids scored in the 90s, a quarter of the kids scored in the 80s, a quarter of the kids scored in the 70s, a quarter of the kids scored in the 60s, right? I'm getting rid of the highest 25%. That's all the kids that scored in the 90s. I'm getting rid of the lowest 25%. That's all the kids who scored in the 60s. So I might say, oh, the interquartile range of the scores on this test that I just gave was from 70 to 89. Okay, that's the middle 50% of the class scored between 70 and 89. The pros are that it's not so influenced by extreme scores like the range is. The cons is it doesn't really tell us about how variable the sample is because we got rid of half the sample, right? We got rid of that top quarter and that bottom quarter. It may estimate central tendency better than variability. We might use it when we have extreme scores or skewed distribution. I'm on slide 8. It doesn't use all the data, so if we report the interquartile range, we might want to report the full range along with it. Okay, so let's go back and talk about notation again. Now, we use different letters when we're talking about a sample versus the population. When we're talking about a sample, we're going to use our regular A, B, C, D, E, F, G. When we're talking about a population, we're going to use Greek letters. Okay? This is what makes reading statistics textbooks so like intimidating. So they throw in all these Greek letters, all right? And sometimes they have to do with terms or what we call parameters related to the population. Okay. Sometimes a particular statistic is given a Greek letter, but sometimes they relate to the population versus looking at a sample. So, for example, we use a capital M or an X bar to talk about the average score, the arithmetic mean in a sample. But we use mu, the Greek M, to talk about the mean of a population. So X refers, like we've mentioned, X refers to each individual observed score. N refers to the number of observed scores. And deviation is the distance between a particular score, right? A particular X, an X sub I, let's say, and mu, or the mean. Okay, and here it's the population mean. If we could average all of the deviations, the distance from the mean to some particular score, if we could average all of these, we'd know how closely grouped or spread apart the scores are, right? Because we'd know how close everyone is to the mean. The distance between a score and a measure of central tendency would be notated as x minus mu or x minus x bar or x minus m. Okay? That's the difference between some individual score and the mean. Can we average those deviations? Deviation is just this distance. Can we average those deviations? Let's try it. So, average deviation. If we're going from an individual score to mu, right, take that difference. If we're going to take an average, we know an average is the sum of all the values divided by the total number of values. So that we get the average deviation is the sum of all these differences, and I'm looking at the bottom box, the sum of all these differences between individual scores and the mean divided by the number of values, okay, the number of scores that we have. So there's our average deviation, but does it really work to do that? Let's see. I'm on slide 13. Let's say we have 3 test scores, okay? And this is my sample. My sample was 3 test scores, 45, 50, and 55. Well, what's the average? What's the mean? 50. Easy, right? Now, what's the average deviation from that mean? The student who scored 45, if you do 45 minus 50, you get negative 5. 50 minus 50, you get 0. 55 minus 50, you get 5, right? Positive 5. If we're going to talk about adding these together, adding all of our scores, we get 150. 150 divided by 3 is 50. That's our mean. Okay, that's our average. What's the average deviation? Let's see. We're adding them all together, all of these. We got to get the sum, minus 5 and 0. Minus 5 plus 0 plus 5. That's 0. 0 divided by 3 is 0. Okay, so wait, because some scores are going to fall below the mean, some scores are going to fall above the mean. Okay, the deviation on of the scores that fall below the mean from the mean, if you all those negative scores, all right, are are going to add up to the same thing, that the deviation above the mean. And so you can't really average the deviation because you have these positive deviations and these negative deviations, and they cancel each other out. Um, so how do we solve that problem? If we can't use the average deviation, it's always going to add to zero, right? Somebody got the idea to square the deviations. All right, now they no longer add to zero and we can average them. And it must have been a mathematician because I don't think the rest of us think of, let's just square the number and that'll solve the problem. But it does work, right? It solves the problem because you won't have the negative numbers outweighing the positive numbers if you're squaring the numbers. Um, okay, they no longer add to zero. We can average the sum of the squared deviations. Try saying that fast. And this average of the sum of squared deviations is called the variance. Okay, the variance. Um, we take each deviation, it was -5, 0, and +5. We square it, we would get 25 plus 0 plus 25, right? We add, we square each of them, we add them together. 25 plus 0 plus 25 is 50. And then we would divide by the number of data points. In this case, it was 3. So it would be 50 divided by 3 would be the variance of that very small data set of test scores that we were just talking about. And the way it's shown is the sigma squared. All right. We use this formula if we're measuring every individual in the population because you see that mu means that we know the population mean. Now we're gonna gotta modify this formula. It might be a little confusing. If you're taking a sample, the previous calculation is biased when you're trying to estimate the population. The reason is that we use numbers in our sample to calculate the mean, and then we use them again in our formula. If you want to know more details, I put a link there to a YouTube video that gives a pretty good explanation. If you're using a sample, right, and your variance is denoted not as sigma but as s, okay? S squared, your variance, you're going to divide by n minus 1. Okay? It has to do with degrees of freedom, which, yeah, I thought meant something totally different than it means in statistics world. But anyway, you're going to divide by n minus 1. Okay, so some individual x minus the mean of your entire sample. You can take each deviation, square it, add up all those squared deviations, and divide by n minus 1 to get the variance. But the variance is in these square units, right? So I have 50 divided by 3. It's not actually in the units of whatever it was that we were studying. Where's my calculator? To get back to our units, we want to get the square root because that kind of makes more sense. Oh, here it is. Okay, so remember we had our sum of squares was 50. Um, and so our sum of squares was 50. Let's imagine that was our entire population. Let's divide by n, divided by 3. 16.67. And then let me get the square root of this. Does that work? I can't. I have my special, scientific calculator. It's been a little while since I've used it. 16 points. I get 4. Okay, that makes more sense, right? To say like the about 4 points is about how far the numbers are from the center, right? Because one was right on, and then two were 5 units away, right? So we're gonna say, about four. We had three scores, not a whole lot of scores, but you get a sense that somewhere between 0 and 5 is the average deviation, or the standard deviation from the mean of your values. Okay, um, it's basically in the same units as your original measure. And Carl Pearson devised the standard deviation in 1892. So this was one of the first statistics um, that was developed, right? And all statistics were invented by somebody somewhere. Okay, so that's important to know. Um, okay, so let's go into the next. Standard deviation, I bet you've heard of it. So let's talk about visualizing dispersion. A histogram is a great way to visualize data. Okay, let's say these are scores on a middle school test at one school. The mean is 80. Most of the scores fall within 10 points of the mean. Okay, but it would be hard to compare this histogram to other schools, right? Let's see. So, because you'd have like a whole bunch of like graphs of histograms, histogram, 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 histogram. You know what I mean? It would be hard to kind of like see. But let's say we wanted to compare a few schools. We would use a box plot. Box plot is a display that shows the center and variability of the distribution, and you almost never see box plots in the real world, but you might see them if you're reading a research report. And I've written research reports where I put box plots in, and it allows the comparison of multiple distributions, as well as drawing attention to outliers. It can also help you screen data for errors, because if you have a like crazy outlier, it could be that somebody entered in the wrong number when they were putting in the data in the computer. Okay, to create a box plot, first you would find the median or the 50th percentile and draw a line. Then you'd find the top and bottom 25th percentiles or quartiles. So the 25th percentile and the 75th percentile, and draw them as the top and bottom of a box. You'd multiply the interquartile range by 1.5 and add or subtract from the quartiles to draw the fences or tops of whiskers, and any remaining points are outliers. And nobody ever does this by hand. We would have a statistical program do this for us. And we would have, specifically, we would have SPSS do this for us. Okay. And here's some examples, and I want you to see them so that you're reading a research report, you know what you're looking at. This box plot shows that if you, let's say we were doing some kind of study, and the we were plotting the race of the respondent when something happened in their age, race by age. Okay. Um, Whatever this study was about, I don't know, the General Social Survey, whatever this study was about, the almost everybody, white, black, or other, whatever this event they were talking about in this study, it happened when the person was around 40 years old. Okay, because I can see that these lines, this median, is hitting around 40 years old. Okay, or maybe it's that most of the people who filled out this survey were 40 years old. Okay, that seems likely. But there was a range for each of the races, white, black, and other, each of the racial groups. There was a range in terms of when, who was filling out the survey. But you see, on average, they're about the same age. Most of the values are similar. The boxes look similar. The whiskers look fairly similar. Okay, so if you wanted to say, hey, I had about the same number of younger and older um, participants in my survey who were white as the number of younger and older participants who were black as the number of younger and older participants who identified as neither white nor black. Okay, you could say that. Here's another box plotting example. This is from a paper that I did with a colleague. It actually it actually has been published. It was published just last year, um, and and you can see there's some the boxes are not all at the same level, right? And what we showed in this paper was that first year teachers who had had a coach, an instructional coach at their school, were much less likely to leave education. They're much more likely to stay as teachers if they had if come they were much more likely to come back for a second year of teaching if there had been a coach in their school. So this was the probability of leaving. And you see when where there's no coach among first year teachers, where there's no coach, the probability of leaving is higher than the probability of leaving among first year teachers here, this first two sets of box plots, than the probability of leaving when there is a coach. Okay. When do we use these measures? Okay. So range and interquartile range. When you're reporting the median as your central tendency, it's very common to report the range and interquartile range. You're going to use it with ordinal data, and you're also going to use it with interval and ratio data, particularly when that data is skewed. Okay. Variance and standard deviation you report alongside the mean. Usually you report one or the other, standard deviation being the most common. Um, it's particularly useful with interval and ratio or continuous data when that data is symmetrical and unimodal, one mode. Okay, so one hill. Okay. Oh, and that's it. That's it. That's it for variability. The most common measure of variability that we report is the standard deviation. Okay, and usually we let Excel figure it out or SPSS figure it out. Okay, that's all for now. See you next time. Bye bye.